Let's see. Not Mark. Can you turn this set of lights off for me, please? Okay, we want to get into the atom. Really, really fascinating. I mean, critical to physics, chemistry, biology. Actually critical overall. I mean, the word atom comes from a Greek word which means uncuttable, and it goes all the way back to 500 BC. Democritus, a Greek philosopher. This is a time when knowledge wasn't cut up into pieces like we do today. What do? We cut knowledge up into pieces. I don't know if we know too much. We have specialized. You're specializing. Democritus didn't specialize. As they philosophized, it was everything. It was the universe. It was matter. It was emotions. It was philosophy. It was ideas. It was the mental, the physical, the spiritual aspect of life was all being considered as one whole. So Democritus, they were thinking about what is this stuff that we're standing on, that we're breathing? What is it? And he just postulated that we would eventually find that all matter was made up of uncuttable particles, that we would get down to a particle level and find out that you can't divide those particles any further. So atom is a Greek word for uncuttable. And it doesn't start taking on some great scientific significance until almost, 2,500 years later. We're going to be talking about Dalton, John Dalton, in the early 1800s. So about 2,000, 2,400 years later, they're getting down to a little bit more scientific view. From Democritus to Dalton, we had alchemists. Yeah, you can actually see chemist in the word. And what were those chemists doing, those alchemists doing? They were trying to convert everything into gold. They were obsessed with the quest of converting, copper. That's pretty close. This is really shiny. That's kind of looks like gold. It's a little dull, but maybe we can convert it into gold or zinc or iron or anything. And so that's what alchemists went after. And they actually started doing some chemistry. They could dissolve copper in nitric acid and reclaim the copper. And so it's trying to figure out, can we get the copper into gold? So that's alchemy. And then with John Dalton, and John Dalton is considered the father of the atomic theory. John Dalton, father of the atomic theory. Dalton's atomic theory. And it's this, he publishes this book in 1808. Now we're talking about a man who was the principal of a school, a young boy actually. He was the principal of a school, I think, at the age of 15. Got his got a degree from university at like 18. And so we're talking about a pretty mental guy that did a lot of thinking. And with the record being set on the rain, Dalton would have loved that. He recorded the weather data that he could get his hands on almost every day for over 45 years. He was a meteorologist, or not a meteorologist, but he was fascinated with weather. And what does weather have? Wind, rain, pressure, sunlight, and precipitation of different kinds. And so he kind of tracked that, and he ended up being pretty fascinated with the atmosphere. The atmosphere actually giving rise to a lot of the weather. So he starts this Dalton's theory of atomic theory. What are atoms? And there's 5 postulates atoms of the same element are identical. All atoms of a particular element are identical. So some of these things are going to seem pretty simple, and oh yeah, that makes sense. But it wasn't obvious in the early 1800s. So what he said is everything is made up of atoms. And what distinguishes one thing from another thing, one element from another element, are the atoms that make it up. So we can basically get down to an atom, a tiny little particle, that is going to have the properties of that element. So atoms of different elements are not identical. The atoms of another element are different from the atoms of the first element. They are different. We'll get back to that. So postulate 1. Matter is composed of small particles called atoms, and an atom is the smallest unit of an element. And that's true. It's not the smallest. There are subatomic particles, but they don't have the properties of the element. An electron does not have the properties of iron. Only an iron atom has the properties of iron. The subatomic particles don't express the properties of that element. So that's postulate number 1. Postulate number 2, all atoms of a particular element are identical. All right, now some of these postulates, we're going to come back and say that at least 3 of these 5 are true today. 2 of the 5 had to be tweaked a little bit. Dalton had no concept of isotopes, and you're going to learn what isotopes are. He had no concept of 2 atoms of the same element that really behave the same way, but they're different masses. Isotopes. Postulate 3, atoms of one element, different properties from the atoms of all other elements. So atoms of a particular element are unique. Iron atoms are iron atoms. There's no other atom like it. And oxygen atoms are unique. They're different from iron atoms. Postulate number 4, can't see it because of the OpenStax logo over there. A compound. Now he's going to a compound. What about when we see something that is not an element, that is a compound, like water? Well, compounds consist of atoms of 2 or more elements combined in a small whole number ratio. So water is always made up of oxygen and hydrogen in a 2-to-1 ratio, 2 hydrogens to 1 oxygen. Copper oxide is an example here. Copper oxide doesn't look like copper. It's a black powder. Copper oxide no longer has the luster of copper. It is a compound where 1 copper atom is bound to 1 oxygen atom. It's a 1-to-1, 1-to-1 ratio. Yeah, there could be zillions of them, but if there are a zillion copper atoms, there's a zillion oxygen atoms. If you have a zillion copper oxides. All right? It's not always a 1-to-1 ratio. It's 1-to-1, 2-to-1, 2-to-3, but small whole number ratios make up compounds. Postulate number 5. Atoms are neither created nor destroyed during a chemical change. You can't create or destroy. Now the alchemists were trying to create another element out of an initial element by chemical means. And Dalton says you can't do that. Chemical reactions are just rearranging the atoms in connection of one element with another element. It's not converting them into a different element. So they maintain their identity, not all their properties. Now they have new properties as a compound, but they maintain their identity as an atom even when they're combined in compounds. So here's copper and in a flask with oxygen, and you react those together and you get this black powder copper oxide, but you still have copper atoms and oxygen atoms now combined with one another. So those are the 5 postulates. There's a slide. Okay, I got to take a look at these. There's a slide with all 5. I got to move that down a little bit. These postulates are still regarded as true. It's the ones with the asterisks. So all matter consists of tiny particles called atoms. Atoms of different elements have different properties. Atoms of different elements combine in simple whole number ratios, and you cannot convert an element into another element by chemical means. It can occur by nuclear means. It's a nuclear reaction that is involved when, for example, uranium gets converted into plutonium, or when an element gets converted into another element, it's something nuclear has happened. Chemistry doesn't occur at that level. Okay, so there's a couple without asterisks. I guess 4 of the 5 have asterisks. Atoms of a particular element have identical properties. We'll get to that in this chapter. What are isotopes? Dalton did not, keep in mind now, Dalton did not know there were electrons. He did not know there were neutrons. He did not know there were protons. He did not know there were subatomic particles. As a matter of fact, his theory would have suggested there is nothing. There's no such thing as a subatomic particle. He believed that atoms was the smallest particle in matter. Now he's right in number 1, or let's see, that the atoms represent the properties of that element. But so you can't break the atom down and still see the luster of copper. You know, that luster, its reaction with oxygen requires the copper atom. But there are subatomic particles in there. And they weren't known in the early 1800s. And that's what the rest of the next 20, 30 minutes is going to be about, is going from Dalton and looking at some key experiments that start developing this atomic theory to what we would embrace today as our theory of really what atoms are, how they're put together, and then that's the basis for how they behave, and even behave chemically. All right, so what we're going to see, we're going to go from Dalton. We're going to move on to some of the key people are J.J. Thomson. And then we're going to go to Rutherford. And then on the scene comes Bohr. And this, Bohr starts pulling it together. And then there is more to it after that. Then we get into quantum aspects of the structure of the atom with Schrödinger and Heisenberg. But here, there are some key experiments right here. And let's just walk through this history a little bit. This is really a fascinating history. So let's see. This is, okay, here, so we're in late 1800s now. Cathode ray tubes. And to bring that into something you might be familiar with, does anybody remember TVs before they were flat screen TVs? When they were fat. Now, they didn't sell them that way. They didn't say, come in and buy our new fat TV. That's what all TVs were. They were big and fat. They were in a big square case. And why were they that way? Well, inside, if you opened up one of those big box TVs, you would have seen a big, huge tube. It would have been in a vacuum inside that tube, and the front of the TV was a coating in there that when electrons hit it, they flashed up and made an image. What they were big cathode ray tubes. That's what they were. What is a cathode ray tube? It is it's creating electrons and firing them down through a tube, and they had a coating in here where you could see where they were hitting. And so they were generating some sort of a ray of a particle stream of some sort, and scratching their heads, everybody, what are these things? All right, so it wasn't just J.J. Thomson that was fiddling around with the cathode ray tubes. They were fiddling around with them all over the world. We got a cathode ray tube. What can we do with this? And what is it? What is it? And they would put different substances in here and get the same effect. They'd get this beam. They'd put a magnetic field in here, and they'd find out that the beam could be bent towards the positive part of that field. So I go, whoa, so this must be a negative, whatever this beam is negatively charged. It's a negatively charged beam. Well, J.J. Thomson is given credit for proposing that this was a subatomic particle. Now you got to realize the paradigm they're coming out of. They're coming out of Dalton's paradigm. There's nothing smaller than an atom. And they're saying, looks like there might be. Something's coming out of all these atoms. It's smaller, it's not atoms, and it's negatively charged. So J.J. Thomson, and like a good scientist, he also thought about the implications of what he's proposing. And the implications were, if this is an atom and something negative, he didn't call them electrons, but if something negative is blowing out of here, we're able to pull a negative particle out of there, there has to be something positive in there that is balancing it out, because it's not charged. The atoms of oxygen in the elemental form have no charge. They're neutral. All the atoms of any element in their elemental form, and you're not looking at the elemental form of very many things. This is one right here. It's aluminum in its elemental form. It's not reacted with anything. It's not a compound. It's an element. The air you're breathing is a mixture of oxygen in its elemental form and nitrogen in its elemental form. They're not reacted to each other. They're nitrogen and oxygen molecules bouncing around, but they are in their elemental form. All right, so in their elemental form, they're neutral. And J.J. Thomson says, we're teasing out a negative particle. There has to be something positive in there balancing that out. And so he is given credit for proposing, he called them corpuscles. Now you might know that more in the biological sense of blood cells and that sort of thing, but his word for them was corpuscles. The word that stuck was electrons. The name for them that eventually stuck was electrons. All right, so in the late 1800s, now their minds are blown. There's a subatomic particle. Are there any other subatomic particles? Along comes Geiger, Marsden, and Rutherford. Geiger, and you've heard of Geiger counters, right? Yes? No? Maybe? Geiger counter? A Geiger counter is a little device that you can use to detect whether something is giving off radioactive radiation. You get near uranium, and the Geiger counter, you just wander around and you might hear a dink, dink, dink. What that is maybe some sort of ray coming in from the sun every so often. You get around the uranium and starts ding, 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 ding. It's counting the radioactive particles that are hitting it. They were working with a radioactive material that could fire out alpha particles. This is more, well, we don't even get to this module, but this has got to do with nuclear reactions and radioactivity. But in the late 1800s, early 1900s, they were starting to, let's see, it was Madam, what's her name? Madam Curie, who did all the work with radioactivity. So they were starting to work with these things. So they said, well, let's take these alpha particles and fire them. I don't even know why. I'm not exactly sure why they thought this would be a neat experiment, but they said, let's pound out a thin foil of gold and fire these alpha particles at the gold. They're trying to make a very thin film so that there's as few number of gold atoms across that film as possible. So they wanted to be real thin. They couldn't get it down to just one gold atom thin, but they were trying to get it down to just as few gold atoms in there. So if you looked at the cross section of it, you might have a gold atom here, and a gold atom there, and a gold atom there, and there. They're trying to get it real thin, and they're firing these alpha particles. I'll just use the Greek letter alpha. And if they had not put their detector screen all the way around this thing, they would have missed the most important part of this experiment. Most of them fired right through. Some of them deflected a little bit, but some of them deflected a great deal. They almost came back at, if you considered this a cannon, like a military cannon at the atomic level, they're firing these strong particles at this thing, and after at it, what is essentially a thin film of paper, and they're seeing some of them bounce off of this thin film and come back at them. And that's what one of the quotes was. It was as if we fired a cannon at a sheet of paper and the cannonball bounced off and came back towards the cannon. So they saw some of these. And what did that mean? Well, that led Rutherford to propose, if we consider this is the way that Thomson viewed things, that there are electrons in here embedded in a kind of a sea of positive charge. Rutherford said, no, I don't think that's the case. It seems like it's more like this. There's a very strong positive right at the center of the atom. All the mass and positive charge is centered there, and the electrons are around it. Okay? This was that was the foundation experiment for proposing this view of things. And so that's where we get our concept of a nucleus. Then atoms have a nucleus that contains most of the mass and all of the positive charge, concentrated, like at a pinpoint. Okay, now just bear with me for a second. Let's say here's a gold atom, and here's another gold atom, and here's another gold atom. I'm drawing that too big. Let's say that's a gold atom, a gold atom, a gold atom. All right, and they're firing these alpha particles at it, and they J.J. Thomson view of this thing would have said there's a fairly uniform mass here. It's like, there's a certain amount of mass there, and these things are going to plow through there, and maybe if they go through 3 atoms, they might be deflected a little bit. They go through or slowed down, whatever. But what is actually the case is this, and that most of the alpha particles blew right through empty space. There was no mass. Right on through. But on rare occasion, an alpha particle actually smacked into the nucleus and came back at the source, bounced off of it because it was so concentrated in charge and mass. By the way, these alpha particles are positively charged too. So they would not only run into mass, but they would run into the same charge and bounce back. So that's what got Rutherford to say this is more what it's like. That the atom is mostly empty space. And that's in line with our view today. The atom is mostly empty space. Like our solar system. Okay, our solar system scopes out a certain, you go out to Pluto and you're, I don't know what you are, 4 billion light years away, or 4 billion miles away to Pluto, not light years. But it's billions of miles out to Pluto. But that is we're carving out as a solar system. But what's in there? 8 or 9 planets. You can argue about that with astronomers. Is Pluto a planet or not? All right, but we got 8 or 9 planets in this huge area of space, and what else is in there? A vacuum. There's nothing in there. Just these planets. Well, that's the view of the atom. We got these tiny little electrons that don't have very much mass, and this very massive, relatively speaking, the nucleus is about 2,000 times heavier than the electrons that are spinning around it. It's massive compared to the electrons, and focused at like the head of a pin. Okay, so that's Rutherford. And that's just another slide on it. Geiger and Marsden were working in the lab. Geiger and Marsden did this experiment. I think at Rutherford's, suggestion, hey, let's do this experiment, and they did it. Here's the results. Rutherford looked over the results, and I don't know how long he had to think about it, but thought, and finally proposed this view. So now where we are is we got a view of atoms have a nucleus that's positively charged and electrons that are negatively charged around it. And here's what I was just trying to draw by hand a minute ago. So there's your gold atoms all stacked up in there, and most of the alpha particles slicing right through, even when it's slicing through the atoms, just slicing right through empty space. But only when it hits the nucleus is it's being veering off course. When it's coming near the nucleus here, being thrown off course, and sometimes way out. All right, so here Thomson's view of it, plum pudding model, Rutherford's model, a nucleus with negative charges around it. And still the question is out there, what are these things doing? Where are they? Why aren't they in there? What is going on here? So Rutherford got this far. And let's see. We want to get to the Bohr atom. To understand where Bohr goes and the key experiments, or the key thoughts that Bohr brings into this picture, we need to understand light a little bit, electromagnetic radiation, the electromagnetic spectrum. The light coming out of the fluorescent lights up here is a part of the electromagnetic spectrum. It's the visible part. A very equal form of electromagnetic radiation that is filling this room right now is radio waves. If someone turns on their radio and they pick up a channel, how are they doing that? Well, there's radio waves all around us. Microwaves in a microwave oven. Infrared rays. If we put on infrared detectors, we could see the heat coming off of your body. You could see infrared radiation come on. These are low energy. These don't hurt you. I mean, don't go crawling in a microwave, but they're not high energy. They don't break chemical bonds. You get into the visible. Now, here what we're doing is we're opening up this visible. What is the visible? Well, red, yellow, green, blue, purple, violet, low energy, higher energy, violet, high energy, and then you start crossing over into ultraviolet, which can hurt you. Okay. Well, X-rays and gamma rays, very, very high energy and very, very high energy. Breaks bonds, ruins stuff, does damage. All right, this doesn't, but this is what we need to understand here. So they took a fluorescent tube, filled it with hydrogen, and ran a voltage across it, and they got light. They saw light coming out of that tube. But when they passed the light through a prism, they did not see a continuous, they didn't see this. They didn't see a continuum of all the colors. They saw that it was made up of 1, 2, 3, 4 colors. That's not real easy to see. All right, so there's 1, 2, 3, 4 distinct lines of color coming from hydrogen. And this is what Bohr started soaking on. Again, many people were seeing this. When you see a scientist like Bohr being touted, it's not like he was working in a lab and he was the only one that saw this. Everybody was seeing it. There was an observation. And from an observation, scientific method is, why is this happening? Why is this? And if they put a different gas in there, if they put in oxygen or nitrogen or whatever, they saw different lines. It's not that every element gave the same lines, but they all did give distinct lines. They had a distinct pattern for each element that they could do this with, mostly gases. And so this was called the atomic spectrum. So this is the hydrogen spectrum for hydrogen atoms, giving this spectrum. What's going on? Well, Bohr proposed, now he's building off of Rutherford. Rutherford said there's a nucleus, there's electrons around it, and the begging question was, where are these electrons? What are they doing? The atomic spectrum started giving a picture, a little bit of evidence about what they're doing. What are they doing? They're in energy levels. They are around, moving around this nucleus in distinct energy levels. Energy level number 1, number 2, number 3. And what is happening? When we put the voltage across the hydrogen, we're bumping its electrons up into higher energy levels. And when they relax back down to their lower energy level, they're emitting light. That's corresponding to the energy difference between the energy levels. Have I lost you? You with me? Following me? Now keep in mind, these energy levels are like the elevator in this building. The elevator in this building. We never get off at floor 1.5. There's no button for the 1.5 or the 1.8 floor. There's very distinct buttons. You get in the bottom floor and you hit floor 3. Goes up, door doesn't open till it gets to door 3. There's no intermediate. Same way here. The electrons don't get bumped to here and fall back down. If they did, they would give this whole spectrum, all light, all kinds of light. Every color of light would come out. But they just sit here until they absorb enough energy to bump up to here. And then when they fall back down, they emit that amount of energy. And it's a certain color of light. That's what you need to just to appreciate about this electromagnetic spectrum, is that your wavelength of light corresponds to a certain energy of light. This corresponds to a certain specific energy, and you can actually calculate it. We won't go into those calculations, but you can. It can be calculated. What is that energy? And so if it goes, if it's coming out here, what would that energy difference be? It's in a specific number. Here's the energies, wavelengths. Okay, so that gives rise to the Bohr atom model, which is a little bit more like the solar system. The Earth is in a certain orbit around the sun. It doesn't just go down to the Mercury's orbit or Mars's or Venus's. It's got its orbit. Mars has its orbit. Venus has its orbit. Atoms can absorb and emit energy via promotion of electrons to higher energy levels and relaxation to lower energy levels. Relaxation energy is observed as a single wavelength of light. Spectral lines are the results of electron transitions between allowed levels. Allowed levels are quantized energy levels, or orbits. These are the principal energy levels right here. What we refer to as principal energy levels. And we will talk about these in terms of what they are. N will equal 1, 2, 3, 4, up to 7. In elements at their lowest energy level state, the highest energy level electrons will be in energy level 7. So uranium, big huge atom, its electrons furthest out from the nucleus are in level 7. Some of them, not all of them, but some of them are out in level 7. And electrons are only found in these specific energy levels. Highest energy orbitals are located farthest from the nucleus. The opposite way of saying that is that the lowest energy levels are closest to the nucleus. And the electrons are always going to go in to the lowest energy level if there is room. There's only a certain amount of room in each energy level, but if an electron will be in the lowest energy level if there is room in there. Atoms absorb energy by excitation of electrons to higher energy levels. Atoms release energy by relaxation of electrons to lower energy levels. So this is what Bohr proposed early 1900s. Most of these men are getting a Nobel Prize for these discoveries, these postulates, these theories, and they, with time, these were saying, hey, this has a lot of merit. All right, this is pretty much, yeah, just ground state. Ground state, the lowest possible energy state for an atom, that would be where none of the electrons are excited into a higher energy level. They're just down in the lowest or ground state, the most natural state for that atom. Oh, and what are some ways that we excite them? Okay, neon lights. What are neon lights? They're not as popular today. We have these electron diode lights now, but 25, 30 years ago, restaurants would have their neon light blinking out there, and it looked that color. What are neon lights? Neon lights are fluorescent tubes filled with neon. And you're putting a voltage through there, and you're exciting the electrons in a neon atom, and they're relaxing back down and emitting an orange light. Argon would emit a blue light. Xenon down here, purple. All right? So why do they use neon lights? I'm sure it's, well, I don't know. It could be the color, could be they're cheaper. Cheaper to put neon in there. Neon's more available than argon or xenon or krypton. Okay, so that's one place where you have seen these atomic spectra. We're exciting the elements, we're exciting the electrons, and they're relaxing and emitting that light. Another place you've seen them is in fireworks. Fireworks. How do you get all those colors? Oh wow, look at the blue one. Oh green, oh wow, look at that. Elements. You put certain elements in the fireworks. Got gunpowder, energy, blows up, a lot of energy is released. It's exciting the electrons in those atoms. The higher energy levels, they're relaxing back down to their ground state and emitting a certain color. So green, barium is coming down. Copper, strontium, calcium, this gives these different colors. That's atomic spectra. Okay, so let's just talk about a few aspects of the atom. All right, so the size of the atom is huge compared to the size of the nucleus. And here's, if you were to take a blueberry and put it on the 50-yard line and call that the nucleus, then the size of the atom is the stadium. Okay, relatively speaking. So there's that much empty space in an atom. It's a tiny little nucleus, and then all this empty space where the electrons are spinning around in these orbitals. But that is the size of the atom, because those electrons are not going to let anything else in there. Even though it's empty space, the empty space, relatively empty space of another atom can't impinge on it because these electrons are spinning around out there. Yeah, so there's 10 to the minus 15th meters. That's the size of the nucleus. 10 to the minus 10th meters. We're looking a little bit at scientific notation here. But that's 10 to the 5th difference. This is 10 to the 5th larger than the nucleus. That means a 1 with 5 zeros after it. 10 to the 5th. 100,000. I guess it's confusing myself. 10,000 times bigger the atom is than the nucleus. All right, the atom, the basic structural unit of an element. It's the smallest unit of an element that retains the chemical properties of that element. It's the smallest unit that retains. So just keep in mind, the electrons, the nucleus, don't reflect the properties of that element. It's the nucleus and the electrons together that behave like an element behaves. All right, there's three primary particles. Now, so far, I've only mentioned two. Here, Rutherford is saying there's positive particles in the nucleus, protons. Rutherford is saying there are negative electrons from the cathode ray experiments. And it was a long time later, in 1930s, that they discovered the neutron. The neutron was a little bit more elusive. Why? It doesn't have a charge. It's neutral. You couldn't kind of deflect it in a magnetic field like you could protons and electrons. So it was a little bit elusive. But they started seeing that, hey, there's this copper and there's that copper. And this copper is heavier than that copper. How can that be? And they said, oh, there's a particle, pretty passive, neutral particle. It has mass, but it changes the weight of a copper atom, but it doesn't change its properties. Its properties are being driven by the proton and the electron. So there's three particles. There's two regions, the nucleus that contains the protons and the neutrons, and then the electrons in orbits around that nucleus. All right, so that brings us to not quite to today, but close to today. This is early 1900s, 1910 time frame. We've got this picture. Protons, they're in the nucleus. They have a certain charge. Electrons outside the nucleus. You can see the charge on the electron, the charge on the nucleus, excuse me, I'm going too fast. The charge on the electrons and the charge on the protons are equivalent, but opposite in charge. So one electron perfectly balances out one proton. Okay, that's worth reflecting on there. It's just not a random thing here. We've got an electron that's equal in charge to a proton, but opposite in charge to the proton. So we designate it roughly a -1 proton, a +1. There is a unit of coulombs, an electrical unit that we could actually say what is the magnitude of that charge. Okay, now if you compare these three particles, so we have these two in the nucleus, we have that one around it. Notice that in atomic here's the actual grams that those particles weigh, 10 to the -14th. So we would have to move this decimal point here and put 23 zeros in front of it. That's an extremely light, but this one already has 3 zeros in front of it, and we're going to put 24 more in front of that. So you can see that the electron is a lot, compare that number to that number, the electron is very light compared to either the proton or the neutron. It's about 2,000 times lighter. These particles, it's like 1,800 times heavier than an electron. So really, when you look at an atom, if you look at the mass of the protons and the neutrons, to the degree of accuracy that we need, that defines the mass of that atom. You can ignore the electron's mass because it's 1,800 times smaller. All right, so when we do talk about how heavy atoms are, we're really going to be focusing on protons and neutrons. If you went to the doctor's office and they weighed you, and they always want to weigh me, I'm always dragging all kinds of things out of my pocket, taking 5 pounds off, just taking things out of my pocket. I can't imagine me saying, "Oh, wait a minute, there's a mosquito on my shoulder." You know, wait, let's wait till the mosquito flies away. That's kind of what we're talking about with electrons. There's these little, tiny, very, very light negative particles out there, but they don't add a whole lot to the weight of the atom. Okay, well, rather than push this any farther, let me pull up that worksheet and you just help me answer these questions. And then what we'll get into on Thursday is the symbol, how we use this symbol to distinguish one element from another one. We have a way of writing a symbol, and just for introducing it is, so oxygen, we would use the symbol for the element. This number is the atomic number of oxygen, and 16 is the mass number of oxygen. This number relates to the number of protons, and like I said, we'll do a deep dive into this on Thursday. That's the number of protons that are in an oxygen atom. This is the mass number, and it's the number of protons plus the number of neutrons. And that's what we're going to look at on Thursday. But for right now, let's, just as a class, help one another out here. The smallest unit of an element is an atom. In accordance with Dalton's theory, the blank is the same for all atoms of the same element. Okay, this one, according to Dalton, now this is the one postulate where he was a little bit off on, but according to him, the mass is the same for all atoms. So as far as Dalton was concerned, every atom of copper had the same mass. It wasn't until the 1930s when we discovered the neutron that we said, boy, there's a heavy copper and there's a light copper. What's going on here? That's neutrons. Number 3, in a given compound, the atoms of its constituent elements are always present in the same, in a compound. Ratio. Very good. So, for example, H2O is 2 hydrogens to 1 oxygen. Atoms are neither created nor destroyed during a chemical reaction. They simply rearrange. What subatomic particle did J.J. Thomson discover? With the cathode ray. Electrons. Okay, remember the cathode ray tube was this beam of negative particles. Describe Thomson's plum pudding model. He would say uniform mass of positive charge with negative particles in it. Okay. We didn't go into Millikan's oil drop experiment. My freshman year at university, I started out in physics, and we had to do that. That was one of our experiments, and we were straining through a little telescope looking at these little oil drops falling. Millikan oil drop experiment. It's a classic experiment to determine the charge on an electron. On one electron. What is the charge on one electron? And Millikan's oil drop experiment. Ernest Rutherford performed a gold foil experiment with what kind of particles? Well, he was firing it at gold foil, but what was he? Alpha particles. That showed the atom is mostly empty space with the positive particles of the atom concentrated in a dense, what did he call it? Nucleus. And here, I think this is Chadwick. We didn't go into that. But he found evidence of neutrons. And he was using a mass spectrometer. And he was able to fire beams of elements at this thing. And he found out that, oh, some of them were deflected this far. Others were deflected further. And realized that the same atoms had different masses. Why are they doing that? Different masses. Okay, I don't know exactly how to use these. I think what I probably will want to do is try to post these ahead of time so you could pull them up on your phone or on an iPad or whatever, and we won't have to print them. You won't have to print them. We can just, sometimes I'll ignore them. They'll just be up there, and if you look down, the answers are down below. Okay? So don't look until after the lecture. All right, this will be just kind of a way to say, hey, what did we get out of this?
Will this be useful?
I'm sorry.
Will this be useful in a review for exam?
I think so, yes. Yes, I do. Because, well, I mean, if I were to say what could be a question on exam, that's definitely one. Link Thomson to the discovery of the electron. Link Rutherford to the discovery of the nucleus. Okay? You could have a question. Who proposed that there was a nucleus at the center of the atom? Chadwick, Thomson, Rutherford, Bohr. And you've got to pick out It was Rutherford. Rutherford's the one that discovered the nucleus. All right? So yes, some of this stuff will be definitely helpful on the exams. Yeah, it's not homework. You could, after an exam, you can look at it and say, I wonder if I could answer these questions. Some of them might not be that good of worksheets. I'll try to take a look at them and post the ones I think are worthwhile. All right. Stay dry. Keep your umbrellas handy. And I'll see you Thursday. Or in lab shortly.